Ferris State University, MFGE 321, Metrology, Lecture 2A, Introduction to Standards, Gauge Blocks, and Gauge Pins. Truth, Facsimile, and Uncertainty. It almost sounds like a movie title of some sort. Well, maybe not. But we as engineers need a baseline understanding of any measurement we take. We will see in our book and future lectures that we can never know the complete truth about a measurement, and that's any measurement. However, we can string together a chain of calibrations that establishes the value of a standard against which we can make a measurement, and that's any measurement in confidence. We'll come to learn more about industrial standards in a few weeks to come here, but in the U.S., traceability for industrial standards will typically be linked back to some facsimile of truth traceable to the U.S. Department of Commerce's National Institute of Standards and Technology, also known as NIST or NIST. Now, NIST states that their measurement work supports the smallest of technologies to the largest and most complex of human-made creations. From nanoscale devices so tiny that tens of thousands can fit on the end of a single human hair, up to earthquake-resistant skyscrapers and bridges, and total communication networks. All right, so pretty much anything that we engineers will work on will fall between these two extremes, and will depend upon NIST for helping us approach the truth of any measurement. When we make measurements, every step of the measurement process is fraught with uncertainty. We will learn how to uncover and deal with this measurement uncertainty, but the fact remains that even though we can become paralyzed with measurement uncertainty, we still have jobs to do. We need to find practical solutions while maintaining a linkage back to precise measurement truth. One facsimile that is commonly applied is the humble gauge pin. Another is the equally humble gauge block. These two devices are the focus of this lecture. We will also uncover the secrets of the mysterious sign plate. Well, maybe not so mysterious once we are done with this online lecture. Pictured here, though, you see a set of gauge pins and an assortment of gauge blocks. You also see pins and blocks in the use of a sign plate. In the title of the slide, I state truth in quotes, as in truth you can hold in your hand. And depending upon the manufacturing expense taken to produce a particular pin or block, you can get closer and closer to the true size or true value of a measurement. And it can be then traced all the way back to NIST using a gauge pin or gauge block. But you can never know exactly the truth of a distance or a mass or a unit of time or whatever. As John Lennon lamented back in 1971, "All I want is the truth. Just give me some truth, man." Well, let's see if we can help. We'll see this slide both in our book and the classroom lecture. But what I want to ever so briefly mention here is how a production gauge can and must be able to trace its measurement uncertainty all the way back to a national standard of some kind. You may be using a fixture or a variables gauge or heck, even a set of micrometers. In any of these cases, you will want to know that you have some access to the truth of a measurement. So a natural question is, who cares? I mean, really, isn't it possible to just be close enough? Do I have to flog myself against the hallowed halls of NIST every time I want to make a measurement? And the short answer is no. No, you don't. In fact, for most of our recorded history, such traceability wasn't considered necessary. As long as Pharaoh's arm was available, you could just go and ask him. Well, maybe if you were a peasant you couldn't, but I'll elaborate more on that in our book. What I have next here, though, is maybe another example of a time that traceability and standards were considered not necessary. Way back when, like is in the 18th century and before, right? When we needed something, we made it. Arts and crafts style. Everything was custom made, custom fit. If something broke or needed to be refurbished or mended, well, we more than likely didn't have a spare parts bin to go to because there weren't really any spare parts. And if there was a spare part, it likely wasn't interchangeable with the part that failed. We see here a depiction of a gunsmith toiling away in his gun shop. An example of his toil is pictured here. It's a simple wood screw. If he needed a particular wood screw for a particular hole, he'd custom make the screw to fit it. If you could look at very old firearms or even look at some old armor up close, you will see many fasteners. But somehow, most are custom and all are slightly different. However, all of this custom work would produce masterful works of art. One could even classify them as industrial art. By the end of the 19th century, the idea of interchangeable parts, popularized by Eli Whitney, not invented, but popularized, had been accepted by industrial nations as the model for industrial manufacturing. One of the drawbacks to this new system, though, was in order to control the size of parts, numerous gauges were needed to check the parts and set the calibrations of measurement instruments. Pictured here is a series of length gauges that would have been used for measurement or calibration. Imagine just how many different lengths you would need to keep on hand, to keep track of, and to manage all the different lengths necessary to build a musket. And this number of gauges needed for complex products and the effort needed to make and maintain the gauges was a significant expense. Additionally, let's say you were a supplier of parts or tools or whatever. Your measurement gauges would somehow need to be related to those of your customers' measurement gauges. The parts you would produce would need to properly fit, be repeatable, and interchangeable with your customers' parts. As usual, fix one problem, another one pops up. Well, it's what keeps us engineers busy, right? Enter Carl Edvard Johansson. Born 1864, died 1943. He was a Swedish inventor and a scientist. Oh, wait a minute. That's the Swedish chef. Here's Carl Johansson. Okay. Now, Johansson invented the gauge block set, also known as Joe blocks, Johansson gauge blocks. You see pictured here a very nice set of blocks. Once stacked together, they can establish a certain desired height to a known uncertainty or tolerance. Now, Johansson's idea, first formulated in 1896, was that a small set of gauges could be combined to form composite gauges that could reduce the number of gauges needed in the shop. For example, let's say you had 4 gauges of sizes 1, 2, 4, and 8 millimeters. You can combine these in any combination, and then when you do this, all of the millimeter sizes from 1 to 15 millimeters can be made from only these 4 gauges. Now, he was granted his first Swedish patent on May 2nd, 1901. Remember that date, 1901. It was a Swedish patent, number 17017, called Gauge Block Sets for Precision Measurement. He formed the Swedish company C.E. Johansson AB in Sweden in 1911. The first Johansson gauge block set in America was sold to Henry M. Leland, a Cadillac automobile, around 1908. Eventually, his gauge block sets would form the basis for establishing linkage to the various national measurement labs around the world, including NIST, well, the precursor of NIST, which was the U.S. National Bureau of Standards, which was founded in, wait for it, 1901. A coincidence? No. The entire industrialized world was grappling with the problems of standards, traceability, and interchangeability right around this time. Johansson found that if 2 opposite faces of a piece of steel were lapped very flat and parallel, 2 blocks would stick together when they were slid together with a very small amount of grease between them. This is called ringing. The width of this ringing layer is about 25 nanometers, and it was so small for the tolerances needed at the time that the block links could be added together with no correction for interface thickness. Eventually, the ringing layer was defined to be part of the length of the block, allowing the use of an unlimited number of rings or blocks without correction for the size of the ringing layer. In the U.S., this idea was enthusiastically adopted by Henry Ford, and from his example, the use of gauge blocks was eventually adopted as the primary transfer standard for length in industry. Here we see pictured on the right hand of the slide, at the top, a production dial gauge, and it's being set up using a gauge block stack as a transfer standard. Below on the right, we see a stack of rung Joe blocks that are establishing a length gauge of known tolerance, and they can be used as a transfer standard. We'll run through a transfer standard exercise using gauge pins in a minute. So what are gauge pins? Well, gauge pins are another form of standard. They don't stack so well, so you'll typically have many pin sets to bridge your needed check sizes. Similarly though, gauge pins are used to establish a reference or transfer standard. Best practice is that when using a set of micrometers to make a measurement, the first thing you do is grab a gauge pin of the nominal size you wish to measure and make sure the micrometers are capable of recreating faithfully that measurement. Again, we'll talk a bit more about that in a minute or so. Both gauge blocks and gauge pins come in classes that reflect the manufacturing tolerance with which they were produced. Their actual size deviation from nominal might be better than the stated tolerance, but never worse. You'll learn in Chapter 2 of our book that tolerance is a form of uncertainty. There will also be bias from true value or the reference value. This tells you which side of the nominal target the tolerance is applied to. The idea of bias is also introduced in our book in Chapter 2, so do make sure you read the Chapter 2 in our book prior to class. As in most cases in life, the more you're willing to spend, the better tool you'll have at your disposal. Here listed are the general guidelines for a gauge pin tolerance for a gauge pin that is 0.338 inches in diameter. Our book includes a table for gauge block tolerance as well as gauge pin tolerance. As for gauge pins, though, the lowest tolerance class pin, which means the greatest tolerance, right, the greatest uncertainty, is the class ZZ pin. These are pretty cheap, and you'd expect a total tolerance for our stated size pin here to be around 0.2 of an inch. One important note here too, as you are bebopping around the plant measuring stuff and checking stuff, be very mindful of whose gauge pins you've grabbed. Let's say you're measuring production processes and you want to grab a set of micrometers and you go to the tool room and they got Class Z gauge pins, and they'll probably be sufficient as long as they're under surveillance and calibrated by your QC department. I would strenuously suggest you do not start digging through your QC department's Class XX gauge pins for floor use. At between $30 to $50 a pin, your quality manager will be less than thrilled to have a pin out there on the manufacturing floor. I'm just saying. It's probably the QC lab's reference standard, so use some care here, folks. Here we see a 0.338 minus Class ZZ gauge pin. If you can read the packaging on our YouTube video, or the resolution of our YouTube video here, you can see that on the packaging it is traceable to NIST. The class calls out how much manufacturing tolerance is allowable for this pin. For a Class ZZ pin of 0.338 inches, we have a total tolerance of size allowed of 0.0002 or 0.2. In the most general of terms, that is equivalent to saying that our pin is made to a diameter of 0.338 inches plus or minus 0.0001. And plus or minus 0.0001, 1/10, equals a total tolerance of 0.0002 or 0.2. An allowable size tolerance is a linear relationship in that the larger the gauge pin, or block for that matter, the larger the manufacturer's tolerance can be. You can just hop down the table and see this. We see too the ever tighter allowable tolerances for the ever better class of pins going from right to left. This table is in your book, by the way. The fact that it is a 0.338 minus pin means that the pin can be no bigger than 0.338 and that all the tolerance is to the minus side. This means that the OD of the pin pictured here must fall between 0.338 and 0.3378. The gauge maker has biased the allowable tolerance to the low side of the nominal dimension of this pin. Why would you do that? Well, because when we choose to use this pin to verify the max material condition of a hole, that'd be the smallest hole, we can be assured that we never accept a hole that is greater in size. It's kind of like an insurance policy of sorts. We'll cover this a bit more in detail in the book and in future lectures. So, Let's use this pin as a transfer standard to make sure our micrometer is working properly. The assumption here is the pin is what it says it is. It hasn't been dropped, it's under surveillance by QC, it's traceable, it's clean, yada, 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 right? We take out our digital mics, carefully measure the pin, and bam! The mic reads 0.33790. Okay, so we now know our mics are reading correctly, and we can use them to measure parts that are close to this range. If we want to measure slightly larger parts, then we might want to check with a slightly larger pin to make sure our mics are acting with good linearity. We'll learn more about linearity in Lab 2. In gauge blocks, folks, they work exactly the same way. One application where gauge pins and gauge blocks commingle is something known as a sign plate. Let's say we want to grind an angled surface, or maybe the part's already been made and we want to measure a ground or machined angle. How does one do this? Do we A, look for a skyhook, or B, find a left-handed screwdriver along with a stout nibbling cup, or C, turn to the mysterious sign plate to levitate our precious angled ground part? The answer is C, the mysterious sign plate to levitate our precious angled ground part. And it's not so mysterious as long as you can chant the mystic trigonometric mantra of So Go Do. Say it with me once. So Go Do. Yeah. We'll focus our energies on the first part of the mystic chant. Sine equals opposite over hypotenuse. So. Quick programming note. The sketch here is provided by Longwood University, the sketch we're going to use here for the next couple of slides. It's a real public university. It's not for profit and the like. And I guess Farmville is a real place and not just a Facebook game of some kind. Who knew? All right, so to set up a sign plate to place a workpiece at an angle requires a sign bar, a couple of gauge pins, and sometimes, most of the time, sign bars come with their own pins, a surface plate, and a gauge block set. You will most likely have either a 5-inch or 10-inch sign bar, wherein the distance listed is the center line to center line of the gauge pins that you'd use with the sign bar. Now, if your sign bar has lost its gauge pins, don't fret. As long as your gauge pins are reasonably close together in terms of diameter, and they're pretty close to the pins that came with the sign bar, they will have little effect on the hypotenuse. However, if the gauge pins are different, right, then you will have to add in their effect on the gauge block stack height. If they're the same size, you're cool. If they're different, you have to compensate for the effect they would have on the gauge block stack height. Okay, so let's say we have a 10-inch sign plate. We've got 2 1/4-inch diameter gauge pins, and they're pretty much what came with the sign bar. So there's no impact there on the stack height, and we want to achieve a 30-degree angle. Or to say another way, we want to have a check angle set up of 30 degrees. Okay. So we'll use our sine equals opposite over hypotenuse equation. I want you to take a moment, pause the video, and work out the solution before you proceed. So hit pause now. All right, did you hit pause? Come on, pause the video and crunch the numbers now. Okay, did you rearrange the equation to what you see here? If so, the problem becomes way simple, right? 10-inch sign plate times the sine of 30 degrees, and you achieve a 5-inch stack height. Easy peasy, right? You will get a chance to work a couple of sign plate problems in your homework assignments that'll go along with this online lecture. Remember, This homework is due at the beginning of class when we next meet. Also, you might see a sign plate problem on the midterm. Hint, hint, so be ready. Okay, last bit here is to mention thermal effects on gauge blocks and gauge pins. Many tool rooms and most QC labs are climate controlled. However, many manufacturing floors are not. In the winter, there's usually temperature parity between the tool room, the QC lab, and the factory floor. However, in the summer in Michigan, different story. So let's say your transfer standards are in the tool room, which is kept at about 70 degrees Fahrenheit. You dutifully set up your sign plate with your gauge block stacked to achieve a 30-degree check angle. You then take your sign plate check fixture out to the manufacturing floor, which happens to be at 80 degrees Fahrenheit. This is where material science and physics take over, and your gauge block stack grows in height because of thermal expansion. I mean, metals heat up, right? And they expand. In fact, pretty much everything expands when it heats up. Something about energetic molecules and the presence of increased energy due to heat. In fact, only water seems to not follow the rules. Once cooled, when water hits 42 degrees Fahrenheit, it begins to expand as it gets colder. And good thing too, because if it followed the rules, life on Earth might not exist. Really. And if this is news to you, ask me in class when we meet again to explain. Anyway, where were we? Oh, right, yes. So we just moved our fixture out to the 80-degree floor from the 70-degree tool room. The gauge block stack grows in length by about 0.0005 or 5/10. And our angle now reads, well, actually it probably still reads about 30 degrees for as well as you can measure it. But it did actually change a tiny bit. However, the gauge block stack did change. If you were working on setting up a variables gauge to measure a tolerance of 0.001 or 1 thou, you just gobbled up half of it from your thermal change. Wow, these things can bite you if you're not careful. And thermal expansion is an inches per degree F thing. On small parts, not so important. On big stuff, it's a big deal. So here we see a windmill power generation station rotor hub transmission assembly. Whew, that's a lot of words. This level of size provides another level entirely to the metrology question of thermal effects on the true value of a measurement. Okay, folks, this ends the first of a number of online lectures I will provide for you part of this semester to try and help fill in the gaps. Don't forget to read Chapter 2 before class and also slug through the sign bar homework. Also, don't forget to wrap up your lab reports and also your variance homework and report. And lastly, I hope you didn't wait until Sunday night before class to see this video, because if you did, ouch, that's going to leave a mark. All right, gang, see you in class Monday night.